Welcome everyone. In the previous video, we have studied the gain compression as a side effect of the nonlinearity of microwave circuits and systems. Now in this video, we are going to talk about two other side effects for the nonlinearity, which are the harmonic distortion and intermodulation distortion. Assume that we are talking about a general nonlinear device or network, which can be represented as a Taylor series from the input voltage. So the output voltage is a Taylor series of the input voltage, such that the output voltage would be A naught plus A1 multiplied by V input plus A2 multiplied by V input squared plus A3 multiplied by V input cube, and so on. And assume that the input signal is a harmonic, time harmonic signal, which has an amplitude V naught and time dependence cosine omega naught t, where omega naught is 2 by f naught, or the frequency of this signal. So the output signal in this case, it would be, as we mentioned in the previous video, it would be A naught plus half A2 V naught squared, which is a DC component, plus the linear component, it would be A naught, A1 V naught plus 3 over 4 A3 V naught cube, which is the linear gain amplification, plus half A2 V naught squared cosine 2 omega naught t. This effectively the second harmonic component, plus 1 over 4 A3 V naught cube cosine 3 omega naught t, which is the third harmonic component. So effectively, the nonlinear device will generate a DC component, will generate the second harmonic, will generate the third harmonic, and so on. So in general, the nonlinear device generates higher order harmonics of the input signal. For the case of an amplifier, these higher order harmonics represent a disadvantage. However, for other applications like frequency multiplier, these higher order harmonic terms represent the main item, or the required signal from the frequency multiplier. So we say that for a nonlinear network, a portion of the input signal at frequency omega naught is converted to other frequency components, DC and 2 omega naught, 3 omega naught, and so on. The first term of the output voltage represents the DC voltage, which will be useful response in the case of rectifier applications. And rectifier applications are basically used in microwave detectors. And also, recently, this rectification effect is used in wireless power transfer. So in the case of wireless power transfer and microwave detector, the dominant term is the DC component, this component. So it is proportional to A naught and proportional to A2 and proportional to the amplitude of the signal square. On the other hand, the voltage components of frequencies 2 omega naughts, 3 omega naughts, 4 omega naughts, and so on can be useful for frequency multiplier circuits. And as we mentioned previously, for millimeter wave generation, we usually use microwave sources followed by a frequency multiplier. And as an example, if I'm interested in generating 120 gigahertz, usually I use a source with frequency 40 gigahertz followed by a frequency multiplier by 3. So the output would be 120 gigahertz. The main item is, or the main idea is how to control the value of A3 and V naught cube to make the third harmonic is the dominant. And on the other hand, I usually use band pass filter to take the required harmonic and to extract the other harmonics. However, for other applications like the amplifier, for example, the presence of other frequency components or the other frequency harmonics will lead to signal distortion if these components are in the passband of the amplifier. So, for the case of a single input frequency or single tone with a frequency or signal frequency omega naught, the output will in general consist of harmonics of the input frequency of n omega naught, where n 0, 1, 2, 3, and so on. I am interested only at the harmonic n equal 1. 0 represents the DC component, 2, 3, 4 represent the higher order harmonics. Often these harmonics lie outside the passband of the amplifier, and so don't interfere with the desired signal at the frequency omega naught. But in general, it is required to minimize the amplitude of the higher order harmonics in the case of some applications like the amplifier. Another problem due to the nonlinearity is the intermodulation distortion. In the previous case of harmonic generation, we were talking about a single signal with a single frequency. What will be the situation if the input signal consists of two signals simultaneously with two different frequencies, such that the input signal it would be V naught cosine omega 1 t plus cosine omega 2 t, or it can also be represented V1 cosine omega 1 t plus V2 cosine omega 2 t. So we have two signals with two different frequencies. The combination of these two signals is the input signal for the nonlinear device. In this case, the output of the nonlinear device, according to the representation of the nonlinear device, V out is A naught plus A1 V input plus A2 V input square plus A3 V input cube, and so on. It would be as follows. The V output would be A naught plus A1 multiplied by V1 multiplied by cosine omega 1 t plus cosine omega 2 t plus A2 multiplied by V naught squared multiplied by cosine omega 1 t plus cosine omega 2 t, all of them is to power 2, plus A3 V naught cube multiplied by cosine omega 1 t plus cosine omega 2 t, all of them to the power 3. Now, by expanding these higher order terms and by using trigonometric relations of the higher order terms of the cosine and the multiplication of two different cosine, so we can simplify the output signal to be as follows. A naught plus A1 V naught cosine omega 1 t plus A1 V naught cosine omega 2 t plus half A2 V naught squared multiplied by 1 plus cosine 2 omega 1 t plus half A2 V naught squared plus multiplied by 1 plus cosine 2 omega 2 t plus A2 multiplied by V naught squared cosine the difference between the two frequencies, cosine omega 1 minus omega 2 t plus A2 V naught squared cosine the summation of the two frequencies, cosine omega 1 plus omega 2 t. So the second term or the square term will be expanded into these four terms, On the other hand, the cubic term will be expanded into these terms. We can note that the square term consists of a DC component and a component proportional to 2 omega 1 and component proportional to or has a frequency 2 omega 2. Component has a frequency omega 1 minus omega 2, and the final component consists of frequency omega 1 plus omega 2. For the third or for the cubic term, we have a term has a frequency omega 1. We have another term has a frequency 3 omega 1. In a similar way, we have a component having we have a component has frequency omega 2, and another component has frequency 3 omega 2. In addition, we have here a component with a frequency omega 2 and frequency omega 1. We have frequency components of 2 omega 1 minus omega 2 and 2 omega 1 plus omega 2. Similarly, we have components with frequency 2 omega 2 minus omega 1 and 2 omega 2 plus omega 1. Okay? From the point of view of frequencies, usually the value of omega 1 and omega 2 are quite close to each other. And the multiplication 2 omega 2 and 2 omega 1 and 3 omega 2 and 3 omega 1 are much higher frequency. So they are usually outside the operating bandwidth of the system or the amplifier. So the component 2 omega 2, 3 omega 2 and 2 omega 1 and 3 omega 1 are usually away from the passband. Also, omega 1 plus omega 2, it would be nearly of the same order of 2 omega 1 or 2 omega 2. So they are actually outside the band. In a similar way, 2 omega 1 plus omega 2 is of the same order of nearly 3 omega 1. In a similar way, 2 omega 2 plus omega 1 is of the same order of 3 omega 1. So they are outside the operating bandwidth. The only terms which will be inside the operating bandwidth will be 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. These two terms actually are quite close to the value of omega 1 and omega 2. So effectively, if I have an input with omega 1 and another input of omega 2, and these two inputs are simultaneously input at the input port of the nonlinear device or circuit, we have output omega 1, we have output omega 2, we have output 2 omega 1 minus omega 2, we have an output 2 omega 2 minus omega 1. These two terms actually represent the interference or the intermodulation interference inside the nonlinear device due to the two-tone signal. So we say that it can be noted that the ratio of the amplitude of the third order intermodulation A3V naught cube, A3V naught cube product, we have 2 omega 1 minus omega 2 or 2 omega 2 minus omega 1 to the amplitude of the third harmonic 3 omega 1 and 3 omega 2 is nearly 3 times of this component. So effectively, the third order harmonic will be nearly 9.54 dB less than the power of the third order intermodulation. How it has come? Effectively, here the amplitude of the signal is 3 times the amplitude of the third order harmonic. The amplitude of this signal, the intermodulation signal, is 3 times the amplitude of the third harmonics. By taking 20 log the ratio 3, we can find out the power ratio is 9.54 dB. So the third harmonic is less than the third order intermodulation by 9.54 dB in the ratio of power. Now, let us see the different components. As I said, we have the DC component with a frequency equal 0. And we have the original two components, omega 1 and omega 2. In addition, we have components which are proportional to omega 2 minus omega 1, and other components proportional or with a frequency omega 1 minus omega 2. For both cases, they are quite close to the DC component. So omega 2 here is greater than omega 1, but the difference here is very small value. On the other hand, we have components with frequency 2 omega 2 or 2 omega 1 and 2 omega 2 and omega 2 plus omega 1. All of these components will be around 2 omega 1 or 2 omega 2. This actually has higher frequency than the original signals. So by using a simple band pass filter, we can select this signal from the DC component and the higher harmonics or the higher frequency components. In addition, we have the third harmonics, which we have 3 omega 1, 3 omega 2, we have 2 omega 2 plus omega 1, and we have 2 omega 1 plus omega 2. So all these components have higher frequency components more than even the second harmonic. So by using a band pass filter, these components can be extracted from the output signal. The main problem comes from the third order harmonic intermodulation, which is represented as 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. Effectively, these two components, as I said, they are proportional or they have frequencies which are quite close to the original frequencies. So if I'm going to use a band pass filter to select the original signal, usually these two components are taken into consideration. And these two components represent the intermodulation distortion. There are intermodulation between signal 1 and signal 2 to introduce new frequencies, which are 2 omega 1 minus omega 2 and 2 omega 2 minus omega. The amplitude of this intermodulation distortion is 3 over 4 multiplied by the value of A3 of the nonlinear properties of the network multiplied by V naught cube of the amplitude of the input signal. So according to the value of A3 and according to the input signal, we can see that what is the effect of the intermodulation distortion in this case. So for an arbitrary signal consisting of many frequencies of varying amplitude and phase, the resulting in-band intermodulation product will cause distortion of the output signal. Effectively, this is known as the third order intermodulation distortion because actually it comes from the third order term. So we are calling this is a third order intermodulation distortion. Actually, according to the input signal V naught, the third order intermodulation signal, it can reach to be the same value of the input signal or the original signal. So in this case, we cannot discriminate between the original signal and the intermodulation distortion signal. And according to this value, we are going to define some value which is called the third order intercept point, where the third order intermodulation will be having nearly the same amplitude of the original signal. And effectively, our amplifier should be used much below such third order intercept point to discriminate or to differentiate between the original input to signals. In the following video, we are going to discuss what is meant by third order intercept point and what is the relation between the third order intercept point and the 1 dB compression point. And from the third order intercept point and 1 dB compression point, we are going to discuss how to take or how to define the dynamic range of the amplifier or the microwave system. This is what we are going to discuss in the following video. Alright? Okay.